Hello everyone, my name is Cody and we're going to be doing the hello world of convolutional neural nets today. That's right, the MNIST handwritten database. So there's about 70,000 different images that are 20 pixels wide by 20 pixels tall, and it's numbers from 0 to 9. And our task is to try to accurately predict what is written on the image to have the machine predict that. So, before we dive too far into it, when I first started doing machine learning and deep learning, there was a whole bunch of stuff you had to do, and by stuff I mean programming, math, setting things up, making a huge flow. But in today's world, we have libraries like TensorFlow, Keras, all this other crazy stuff that's out there that really helps, and it provides such simplicity to that. So in a handful of lines, we're going to actually be able to create something that's pretty accurate, and is pretty crazy to think of in this day and age. Basically, like, who knew it, kids? So the first thing I want to point out is that I'm using Colabs. Now you can use Jupyter Notebook, Colabs. You could just fire this up in a Python if you want to, but for me, I kind of like seeing the Jupyter Notebook in Colabs because it has a built-in GPU. I'm using a Mac, so the GPU is not necessarily that readily available for me to set up, and this is just the site that I use to record. So check in your runtime, go to runtime type, GPU if you are using Colab. From there, we're just going to import a handful of tools, and then we're going to go off to the Keras datasets. Now, beforehand, this again, you'd have to know about these data sets, and you still do. There's sometimes when I'm trying to find whether there is a corpus out there, and it's kind of hard to find, but these are like classic, very useful data sets that we can all get easily from Keras. So all you have to do is just copy and paste this. It says that it's going to return some tuples, x-train, x-test, y-train, y-test, number of samples, and then 28 and 28, and that's the pixel size. If you would have looked at the description or would have known anything about mints, that's exactly what's going to be happening. So you'll see that right here. Now, I already pre-downloaded this. Apparently, yeah, there it goes, it's just checking. So I already pre-downloaded this, so it may take you a little bit, but while we're doing that, I'm just going to run through a handful of things that I did beforehand that I kind of like doing whenever it comes to a data set. So if I was tasked with this, to predict 0 through 9, and I had this huge data set, the first thing I'd want to do is just like see, what this data set is or was. And when you look at it, it does accurately portray what they were saying in the description. And so then the next thing I do is I just grab, a random image from this group, and I picked 44. And then I printed up what it's going to be training. So it says the label for this is 3. So we know that hopefully when we look at the training data, it's going to be a 3. Now, this is a representation of the training data for kind of how like a computer would see it. And it's word wrapping right now. So if you look, here's kind of the start of the top of the 3. And as we scroll down, yeah, it totally looks like a 3 to me. Even with the word wrapping, it's not that hard to visualize a 3 if you look at the non-zeros. And then just to confirm, we're going to plot it, and plotting it looks like this. So if you looked at one of the previous videos, you'll see me that I've often talked about like looking at pixels like this. And then this is the grayscale version of that. So this pixel right here, this pixel right here is in this very top pixel. So that gives you an idea of, all the lines, and it's showing you right here there's 28 lines. And there's 28 lines here. So now, hopefully it's downloaded. If not, what I want to let you to look at is this link right here. This is a really good example of a CNN. They get it to 99.25% accuracy with very little, training time, which is very like crazy. And you can certainly look at this after you're done looking at the video and seeing what you'd want to add, what you don't want to add, how you'd change it, so on. So moving forward, looking at this, we know, like I saw this right here, and even if I didn't know or hadn't read the documents beforehand, I would know that these are probably things I would want, since we know that there's a convolutional layer that's needed. There's also a pooling layer that's needed. Dense, if you do not know, is just simply another term for fully connected. And it's actually a simpler version of fully connected. But, so knowing that, what we want to do first is the convolutional layer. So there's convolutional layers, pooling layers, and then at the very end, it's a fully connected layer. So let's go ahead and dig through the documentation for convolutional layers. Now I conveniently have it linked here for you. If you didn't have this, you would have had to have gone through and read the documentation until something popped out. In convolutional layers, if you've never, if you know a little bit about deep learning, you would know, or CNNs, you would know that a convolutional layer and pooling layers are important. So if we go ahead and take a look at this, we see conv1d. Okay, so we see conv2d, and that is images. That is exactly what we want. So it looks like there's a handful of things we need to do. We need to do a filter and a kernel size, and then if we look, all this other stuff seems to be filled out. Now, as a general rule of thumb, a stride of 1 is what you're just going to want to leave it as, unless you start fine-tuning things. When you start looking at like improving, accuracy. But when you're first starting out with a data set and you're trying to do a CNN, there's no point in changing the stride. And if we look over here, yeah, this looks like all pretty much default generic stuff that's set up. One thing that will get you hung up on this, and this is a great example of understanding and knowing your data, which I think everyone should be doing first, and then going on to looking at deep learning methods. Like everyone, once you start learning deep learning, suddenly you just think everything needs to be deep learning, and it's not. Same thing with CNN. Once you start learning the CNNs, pretty soon everything starts looking like a CNN problem. And it's not. There's a lot of easy solutions to things that CNNs and other, deep learning models just get in the way sometimes, and it's better to be simple. But in this situation, assuming that we looked at the data, and if you didn't, I did, and I got hung up on this even. So what we need to do is we need an input shape. So when we're using this layer at the first layer in a model, you need to be able to input the shape. And that's basically by saying input shape equals 128, 128, and 3. So what this is representing is the pixel width, pixel height, as well as the channels. Channels would be 3 if this was a colored picture, but let's look at this. This is grayscale. So we're only going to have one channel, and it's going to be from 0 to 255. Otherwise, it'd be red, green, blue, and each red, each green, and each blue would be 0 to 255, depending on what color you're trying to make. Okay? The filters are basically the output, and for the first layer, you generally want to just keep it the exact same as the image, and then you can change it however you want. Feel free to experiment with this. That doesn't mean that it's 100% true. It doesn't mean that you don't have to do it. Try to experiment with it, and leave a comment if something was interesting that showed up. The kernel size is basically the height and the width of the box, patch, whatever you want to call it, that is going to be cycled through in the scrolling section. So remember, when there's a vector of the image pixels times the filter or feature detector, that's what kernel size really means in this situation. So let's go ahead and copy this, and let's put it down here. And there's going to be a reason why I'm putting it down here. It may not seem like it at first, but there's going to be. So we're just gonna copy that so they don't have to go back to it. Okay. So the first thing we want to do is we want to look at our rows and our columns and our channels. 1. So we got 28 pixels going across, we got 28 pixels going down, and we've got one channel. So now the next thing that we have to do, and this is what caught me up, is that the MNIST is actually missing the channel aspect of it. So let's scroll back up and look at the shape. And where's the shape? There we go, the shape right here. It's 60,000 of the samples, 28 pixels by 28. We don't have the channels, and so we want to have that shaped in there. So let's go ahead and reshape X, train shape. Whew, I cannot type. Now there is a better way to do this, and if you want to debate the methods, feel free. Because for example, I could do rows, columns, channels, and now I could actually loop this into kind of like a base model design where instead of having a hard-coded 28 pixel by 28 pixel or samples, this is the sample size, and then 28 pixels by 28 pixels by one channel, which is hard-coded here as well. We could even do this if you want to. Except for that would be hard. Tests, sample size, and then we could just do this. You could come up with some way to dynamically create a function so that you have kind of like this base model so that you're not, always inputting these things. But again, it would depend upon your data, how you capture this data, and whether that made sense or not to run through it that way. Let's see. Let's see that. Let's make sure we have no errors. We have no errors. One other thing I'm going to add is input shape, and I think I spelled that wrong below it. Let's take a look. So what we want to do is 28, 28, 1. We might as well just throw that up there. Otherwise, when we get down here, yeah, I think I put input size, input shape. Shape, let's double check. Yeah, it's input shape, and I think I put input size, which makes no sense. Okay, so now we so now one of the things that's you should always think about when handling data is normalizing. It's one of those things that not talked about often, and I think since we're already reshaping things and doing some data manipulation, we might as well just finish the data manipulation and figure this out. So right now we have a few problems here. We need to change the type to float, and then we need to normalize. And the reason why we want to do this is because data right now is sitting at 0 to 255, and if we wanted normal data, it would be from 0 to 1. And this just makes it kind of with machines, it just helps them not see such drastic changes in the data. So let's just do xtrain, and I think it's float 32. Perfect, no errors. So now, since xtrain is just, let's just go ahead and do some testing on this. Oops, what am I doing? Print x train.shape, print x test.shape. Okay, so now we have that. So now what we want to do is we want to go ahead and take a look at the let's just double check that we have this. So train, and remember we have image. And then if we go up here, we can completely see that there's 1, 2, 3, 4, 5, 6, 7. Okay, so we see that the pixels start firing off right here. Otherwise, we won't. Everything's 0, so we really won't know if we had an impact on any of this unless it's 0. So here, 163, all that jazz. We'll print it off, and then we'll do 7. Why is image not? It has to be processed. Okay, so there we go. So now we look at this, we see that instead of seeing like 255 or 254, we see 0.992, right? So if we went to 8, we'll see the same thing. We'll see a series of numbers that are much smaller than 255, and that way we don't have to worry about the machine kind of maybe overthinking certain aspects of of our language, of our model. Okay, so so this is the general concept that we're trying to do. If we were to look at sequence, model sequential, we see that there's a handful of other techniques that we can add into it, right? So we see predict on batch, fit generator. We're seeing a bunch of these things. And what we really want to do is try to instantiate it. So let's take a look at this. So we see we can compile, see we can do fit. Let's go look at our example, and let's see if it does like a model equals sequence or whatever. Sequential. So there we go. So yeah, so it does something like this. Now there is a way for you to take all of these pieces and just pluck them in here, but I think that becomes really hard to look at. So if we were to do this, we were to do model equals sequential. Okay. Oops, underscore. And so now, if you look at this, this is like a Keras specific thing. If you do model.add, we can go ahead and do that. So model.add, and we'll just get a backspace after that. If we did everything right, we found no errors. And did I do filters? Did not. Let's do that right here. Actually, you know what? Let's take this. No, let's leave this right here. Let's do filters. It's 28. Let's do kernel size goes 3. So let's just rerun that one. We can run these over again. It's not going to hurt it. There we go. And now let's make sure there's no error. Okay, there is no error. Okay, good. Okay, so now if we go ahead and we take a look at pooling, let me see if I can find it. Uh-oh, I can't seem to find pooling. Pooling layers. If we take a look at pooling, we see we have max pooling 1D. And this again is for like a time series data, so we don't need that. And then if you look at max pooling 2D, you see that this is a max pooling operation for spatial data. Now, if you do any reading on CNNs, there's a lot of reading that says max pooling is kind of like just your generic go-to place. I think it depends on the data. I think it's important to have a general idea of how it works, but if you look, there's only a handful of other pooling tools that are actually in Keras. So if you go ahead and take a look at some of these and Google them, you can actually get a pretty good idea of like where or when you should be using them, because most of this is documented fairly well. So for our situation, we're going to do max pooling, and we're going to use the 2D. And what we need at a minimum is the pool size. And it's already defaulted to 2 pixels by 2 pixels, but I kind of like having a bigger pixel move over size. Now that doesn't mean you can't. Oops, let's go ahead and copy this. That doesn't mean you can't. You can certainly do that. So let's do model add max pooling 2D pool size equals 2. Let's just do 3 and 3. Now the fully connected. I expected full parsing. Let's go ahead and take a look at this. Model add. There we go. Okay, so let's go ahead and take a look at this. So the fully connected layer, and as you can tell, I'm not going to this is a very simple, very simple convolutional neural net. It's you have one convolutional layer, you have one pooling model or layer, and then we're going to go and we're just going to go ahead and we're going to try to make the fully connected layer. So the fully connected layer, basically, before you go into this, this is like, oh, it sees the input, and then it makes a prediction, and then it sends it to a probability, a prediction like percentage of, is this a 4, 3, or 5? And so it's basically saying 4 equals 99% chance that this is a 4, and then it spits it out. So what it does is it takes all of the gibberish math that's going on in the convolutional pooling layers that are very convenient to be able to be left alone, and it essentially flattens it and squishes it down into one single kind of number, which then after everything kind of gets looked at, it starts connecting everything together. And Keras makes this super easy. So we're going to add, what we want to do is we want to flatten it. So if we go ahead and go back here, and we okay, so apologize, my system froze up a little bit, so I thought I'd just pause it. But if you look through, come on now, might frozen up again. If you look at flatten, it's got a bunch of different ways that you can flatten. And if you just go straight to this, you'll see that there's just a simple call to flatten it. And so you can kind of be like, is this? It's a little confusing. Is this the right way to do it? And really, this is kind of like, for me, I kind of view this as kind of the downside to the downside to having it as simple of a library as possible, because this is really prepping it to connect. So if you were to look at this, it flattens a tensor. Now you wouldn't know without understanding how fully connected layers work why there's a tensor involved or why it needs to be flattened. But essentially, what we're doing is we're taking the tensor that mathematically comes out to be kind of your width and height minus the filter size of 1. And then there's just this number of filters. So as detectors and layers and filters keep piling on, there's this unique math formula that comes out. So every time it's being outputted, this is the number that kind of comes in. And so it's for multiple layers of convolutional and pooling layers, you want to have this. You don't want to flatten your tensors. But then when it becomes fully connected, you actually want to flatten your tensor. So without having the background of like why are we doing this? Like why are we flattening a model? Like this doesn't seem to make any sense. You're not going to know. So unless you physically had to have flattened it at some time, it's not clear, why you would why you do this. You would just have to kind of just build this out. And the same thing with like you know, like we're basically creating a rate of dropping out so that we don't overfit something. It's kind of a pain to do this sometimes, but did I backspace that? I must have. Let's just drop out of 0.02, which is 20%. And this is just to, again, to stop overfitting. So without really going into the details of why, you know, we use dense as like a simpler version of fully connected, and we're adding a dropout rate so that things aren't overfitted. And then we're going to do it kind of like this one more time. This is like the final, you know, so basically we have, when you're thinking of this as images, we're trying to figure out 1, 2, 3, 4, 5, 6, 7, 8, and 9. So these are all of our options, right? And the fully connected layer is trying to take the information that we have and connect it with these kind of things. So, in some intents of this, adding a dense layer that's 10. The reason for that is, how do I spell activation? The reason for that is because that's going to be the outcome that we're trying to look for. Those are essentially those are the classes. Okay. So now let's let it run for a little bit. I think this is because Keras is going to, I think Keras updated. I'm not sure why it's doing that. It's there. It's not 100% clear to me why it's there. So the last thing we need to do for, well, not the last thing, but one of the other things that we need to do is we need to fire off the compile. So it's, you know, there's an optimizer, there's a, but nope, you don't need that. There's a whole bunch of other things that you can do to adjust this. Loss, metrics, all this stuff. So like right here, typically you will use metrics equals accuracy. Okay, that's great. That's something that we're probably going to do then. So let's go ahead and copy this. And let's go ahead and just start compiling it right here. So we'll do a model. Model.compile. And the optimizer. So the optimizer is, you know, without. Here we go. So here we go. So if we look at optimizers, we kind of have a handful of different pieces to it. There's stochastic gradient descent, there's all these other things, a bunch of other stuff. And it's just from knowledge that I know that we want to use Atom. It's just a you know, very, very common type of math, and so you can look up this link right here and read on it, on why it's used. It's pretty interesting if you want to really like start, you know, maximizing your knowledge and how to do this beyond just simply plugging and playing stuff like this. So we're going to use Atom. Our loss is going to be sparse categorical. And again, you can go back here and you can read about the loss, and you can Google, or not Google, but you can search within docs to see why I picked this or why I shouldn't have picked this. And then this one, we're going to do accuracy. Okay. So now let's see if we get a, okay, perfect, no errors. Model.fit. And if you look at fit, it's going to have training data, which is the X and then it's going to have the label of the training data, which is the Y. Then we're going to have batch size, which right now is equal to none, epochs, which is defaulted to 1, and then a bunch of other stuff that when you start getting into it, you can start fine tuning it. But those are kind of the high level important stuff. So what we want to do is we want to make sure that our x equals to x train, y equals to y train, box. Let's do 12, 15. Let's do 15, see what we get. So I think if I did this right, it should spit out some things. Yeah, so now you're seeing, it's starting to do its training, and it's spitting it out so that you can see it live. So we'll just wait here, and if it takes too long, I might pause the video and just let this go through. So I paused the video, and we're back. It ran through its cycle. As you can see, the loss function slowly started going down. That's a good sign. Accuracy almost immediately flew through the roof, so that's really great. So let's truly see if it did. So 98%. Not bad. It's no 99.25%, which is what the demo had, but it's pretty good considering that it just went through a handful of events. So let's just go ahead and now let's say so remember that image of 44. Now let's create an image from the testing data. So now when we're checking things, the last thing we want to do is kind of throw some phone's going off. Doesn't matter to me how we, it doesn't matter to me what number or how we do this, but we don't want to throw our testing data away. This is like the data that we use to test it. So we're going to assign new image 100 instead of 44. We're going to plot it out so it's a 6. It's very clearly a 6, right? So let's go ahead and make a prediction. We're going to do model.predict x test. I'm just going to new image. Oops, what am I doing? Image columns. 1. Bring this. So the sample that we're putting in is 1. Then it's the rows, columns, and channels. And now what we do, we print out it predicts 6. So there you go. So you could basically do anything you want. You could do 150. It's a 9. And it's a 9. Let's try 190. Ooh, I think that's a 1. It's a 1. All right, see how that works?